Hello, everyone. Today is February 26th, 2023. My guest today is Dr. Bethany Hudak. Dr. Bethany is a research chemist. Thanks for coming on the podcast.
Yeah, thanks for having me.
You're welcome. So, how did you begin becoming a research chemist?
So I always start with sort of going back to my childhood. I have two older brothers. One of my brothers I just idolized growing up, and he was always interested in science. So he wanted to be a scientist, so I wanted to be a scientist. And just generally throughout school was drawn more towards the math and science disciplines. I do like to read, and a lot of science people don't realize is a lot of writing, so I'm good at that too, but I never was into like history or those more, I don't know, that sort of work. So I was really drawn towards science. And then in high school, I had a really fantastic chemistry teacher, and she was just incredible. And I really enjoyed chemistry, and I decided I'll go to college and I'll study chemistry. So I started college at a small liberal arts school in 2006. So I finished my undergrad degree in 2010. If you pay attention to financial news, you'll know that there was a big economic downturn in about 2008. So there weren't many jobs available. So it wasn't a really great motivation to go to grad school, but I thought, can't really get a job. I really enjoyed lab work. So I just figured I'd go to grad school. I'd keep doing lab work. I'd learn some more. And then, whenever that finished, I'd have a nice job. So, I went to grad school. I had a couple of professors in undergrad who really influenced me to pursue that lab work. So went to grad school, and I met a professor that I worked with there who introduced me to electron microscopy, and I just fell in love. I get to look at atoms on a regular basis, and it's incredible and fascinating, and I just never get tired of that work. And there are days when it's like, oh, I have to go to work today, but the work I do, I find fascinating, and I just love it. So here I am.
That sounds amazing. When you say you get to look at atoms every day, what is it that you see when you're looking at atoms? Through scanning transmission electron microscopy?
Right. So we use a scanning transmission electron microscope, which is abbreviated as a STEM. And we're literally looking at the atoms of a material. We have a sample sitting in the microscope, and the beam hits the sample, and it gets scattered, and we get to see that scattered intensity. So we're looking at the very atoms that make up I look at a bunch of different materials, some electronic materials and other things, whatever people are developing. So it's really cool. Are you familiar with graphene?
Yes, but can you present what graphene is?
Yeah, so graphene is what's referred to as a 2D material, and it's a single layer of carbon. So it's just a long sheet or a large sheet of single carbon atoms arranged in a big layer. So we can look at graphene and other 2D materials and see just single atoms as they're arranged in these materials. And we can look at defect structures. If you think of a sheet of carbon atoms, you can change its electronic properties by introducing maybe a nitrogen atom or an iron atom or different arrangements of the atoms. So we look at that and how it affects the overall properties. But we also look at 3D materials, which are trickier because you have to look at large stacks of atoms at a time. And so if the material gets too thick, then we can't resolve the atomic columns, and we have to thin down the materials. There's a lot of prep work. So we don't get to look at everything, but there are some really cool projects that I get to work on.
What's the thickest sample you can work with?
So the thickest materials we can image at the atomic resolution level are probably 30 nanometers thick. So it's getting down to very thin materials. But we also use the electron microscopes for imaging larger materials, nanoparticles that can be up to hundreds of nanometers in size, or nanowires that can be microns in length. And we have a lot of different spectroscopy techniques that we can combine with the imaging so we know what materials contain. So we look at, right now I'm on a project where we're imaging nanoparticles that we're trying to put different concentrations of platinum on the surface. So we can use the microscope to, after they perform the platinum deposition, image them and use our spectroscopy techniques to see how much platinum was put down, how successful that synthesis was.
Okay. And so earlier you mentioned possibly bringing in nitrogen. Is that to a graphene layer?
Mm-hmm.
And was that a much lower quantity of nitrogen? Because this, you said, more of a sheet of platinum versus maybe just an atom of nitrogen.
Right. So we can, we can image and study things with various quantities. So we can look at single atom characterization and look at a material that contains 99.99% of something, and then you might have one impurity atom, and we can identify that if we are looking in the right place at the right time.
And what have you found regarding impurities and how that affects materials?
Well, there's a lot of known ways that impurities affect materials. So even in electronic devices, they're mostly silicon based, but a lot of devices are what they call N-doped or P-doped. So either putting in impurity atoms with that are negative in comparison to silicon, that have a negative charge or a positive charge, and adding in those impurities affects the efficiency or how well suited your electronic material is for your application. But that's all done at a large wafer scale, they call wafer scale, where you have, you might have a large wafer of silicon and they just put in 10% phosphorus atoms, and then it goes wherever it goes. So the work I do, what we're trying to really nail down and push for is taking these impurities and finding the best place for them and how to incorporate them in an arranged manner in a lattice. So instead of just throwing everything out there and seeing where it sticks, we want to be able to use our electron microscope to position these impurity atoms where we want them to go, where we think they'll be the most beneficial.
And what is a lattice?
Oh, sorry. Yes, a lattice is just a regular arrangement of, in this case, it'd be a regular arrangement of the atoms, or any repeating unit would form a lattice.
Okay. And it might be difficult for people who have never looked at models of nanostructures to understand kind of what it exactly is when you're speaking of maybe a crystalline
Mm,
lattice. Is that correct?
right.
Okay. I'm sure people have seen that model, but maybe they don't have the association in their head exactly. But if they Google, lattice, they'll be able to see. Could you repeat the definition?
Of a lattice, yeah, I would say it's just any repeating unit in a regular arrangement. So lattice doesn't just refer to atomic structure or crystalline structure. You can have a lattice of anything. If you have, a regular stacking of bricks on your house, that would be a lattice of bricks.
Okay. Got it.
Sorry about the birds.
No, that's okay. And before the podcast, you mentioned that those are you have 2 conyers, correct?
Yes.
How long have you had your conyers?
We adopted one in 2020, like September of 2020. And then we just got the second one a couple of months ago to keep the first one company.
How has it been with the second one?
Oh, the 2 birds love each other, but I think they're starting to like each other too much, which is making them a little aggressive towards us. But
Oh, wow.
bird behavior is strange.
Bird behavior is strange. I had a cockatiel when I was younger.
Okay.
They're much stranger than mammals. Once you leave the mammal sector of pets, it's wild territory.
Yeah, it's all just been a very interesting learning. I don't know.
Was there a reason you chose birds instead of another? Are these your first birds?
Yes, these are my first birds. We have 3 cats. So the birds and the cats make an interesting mix, but I don't have the energy for a dog.
Yes. Birds are much simpler, and you can keep them in the cage.
Yeah.
So going back to nanostructures, then so you are attempting to position impurities specifically, very precisely
Mhm.
within different materials, and that is not a simple process, correct?
Right. It's sort of a brand new field. So there's a lot of this sort of came about from the emergence of quantum computing. So as our computing requirements increase and our computing power has kind of stagnated, scientists and engineers are looking for better computers. So one architecture that could really shrink down the size and increase the power of computers is single atom quantum computing, where you can encode an atom, the spin of an atom, to not just be a 1 or a 0, but you can have multiple spin states. So then instead of just a binary system, you can have almost an infinite system, and you can encode a lot more data. And you're also working on a much smaller platform. So this is something that's starting to gain more traction and more attention. So we're looking at how you can position specific impurity atoms or atoms that could be encoded using the electron microscope, so that you know exactly where your atom is. But there's a lot of issues that then come. So this is sort of new territory where we're just learning how we can use the electron beam to position atoms, what kind of atoms it works with, what other materials we can branch off into. And then there's questions about if you can build a material where you have these impurity atoms where you want them, then how do you access them for like encoding or readout? How would you actually build a computer out of it? So we're starting at square one, but maybe something will come of it in 15 or 20 years.
Okay. So the encoding of the atom hasn't occurred yet.
Not in the materials that we've been working with.
Okay. And positioning them precisely allows better understanding of how to encode that material. Is that correct?
Yeah, it provides better understanding of how that impurity atom will interact with the rest of the material, how stable it will be in that position. There's questions of if you have an impurity in a 3D material, how deep below the surface it needs to be, so we can study things like at different depths, what kind of properties we're getting out. So we partner a lot with people doing theoretical calculations because there's a lot we don't know about our systems, but other physicists can prepare models and study theoretically what these materials should do, and then we can try to either use their models to make materials, or they can use the materials we're preparing to make their models. So there's a nice back and forth between theoretical physics and the work that we do.
Okay. And those physics that you're going back and forth with their models, those are theoretical physicists?
That's right.
And you and your work and your team, you're doing the quantum physics behind that.
Yeah, we do the experimental side.
What do you mean by experiment? Oh, but they're doing the theory.
Right.
Okay.
I mean, you could also call that experimental. I guess just generally we break it down into theory and experiment, but that's not to say that the theorists aren't performing experiments. I mean, it's all experimental in science.
Yes, especially at the level that you're at with your projects.
Right.
How do you feel doing these processes that have really never been done and at a scale that really is novel?
It keeps me going. I find it, really exciting. So at this level, everything we're doing is unknown. Even if we're not working in quantum computing, if we're working on solar cells, it's all unknowns. It's all new knowledge that we're contributing, which I find to be really exciting, and it, gets me going to work every day.
I can only imagine. And you said solar cells?
Yeah, I've done a little bit of work with potential solar cell materials.
What type of work?
So it's the project I was imaging for. They were trying to add, again, impurities to a known solar cell material to try to enhance the efficiency. So I was imaging the material to see if they really made what they were aiming for. And unfortunately, long story short, the material they were trying to make was not actually what they made.
What? Okay. And so you're working a lot. You have a website with a list of your projects on it, and there's a long list, over 20, and of various different projects. I see, working with dopants and battery materials to, I believe, I'm not sure, something to deal with capacitance.
Mm-hmm.
And also working with nanowires and relating thermoconductivity with materials. What is your view of dopants and of bringing impurities into, what is the reason we need to do that? Why can't we work with pure materials?
In most cases, in many cases, pure materials are great, but when you start adding impurities, whether it's these dopant impurity atoms or even rearranging the atoms slightly so you can create defects, you can remove atoms, the material just behaves differently. So if we want to tailor our materials to make them more efficient, we can often take a known pure material and then sort of mess it up and make it better.
Okay. And does that change anything in the manufacturing, or does it change something at scale? Do you know?
Yeah, it's quite interesting that we know just by altering things at the atomic scale, your macroscopic properties are completely different. So I find it really fascinating that you can just move things around at the atomic scale, which is just so small, and then it impacts real world applications.
And that is the goal of what the projects you're handling related to precise positioning of impurities for quantum computing to lower the amount of materials, change the process of computing, and eventually at a macro scale, once a process has been developed, maybe decades down the line, who knows, but eventually in pursuit of making it much cheaper for computers to be made.
Right. Or much more efficient for computers to operate. I mean, currently we're running, if you're familiar with like cryptocurrency and how that's harvested, it takes just so many servers and so much energy. And a lot of that is just wasted energy. To anyone mining Bitcoin, it's probably not wasted, but it's a huge amount of energy loss and it's a big drain on our systems. And if we can make computers more efficient, we can save a lot of energy.
Absolutely. Cryptocurrencies are a great use case. Also, people who want to run AI on a local machine, it's, if you want, I've tried to run a neural network on my computer and it's, nearly impossible.
Right. Yeah, and everything's becoming AI driven and data driven. The field that I work in, everything's becoming automated and you have these algorithms that automatically process data, and it's a huge drain on energy sources. And it's even, people just want more and more. They want more automation, more interconnectedness, more autonomous behavior, and it's just going to put a huge demand on our energy storage.
Absolutely. And speaking of energy storage, you've also, I alluded earlier, worked on batteries and different battery materials. What are the current, maybe very high level materials used in batteries, and what projects have you worked on in pursuit of optimizing that energy storage?
Yeah, so you mentioned a bunch of projects that I work on. And I'll just say in my work, because I specialize in electron microscopy and imaging of materials, I have my own projects, which is largely atom manipulation and studying single atoms and characterizing those. But then, yeah, I also work with a lot of other groups when they create a material and need to know what they've made. So I have a lot of projects that vary from batteries and a bunch of different materials. So I'm not always an expert on exactly what they're trying to do, because I just have to know enough to give them results from my work. But there are demands for higher efficiency batteries. So I have done some imaging and some work with groups who are designing better batteries or better energy storage systems. So batteries might, as we know them now, might not be the best storage for energy. So there's been some development in fuel cells that I've been working with that could be more energy efficient or more energy dense and lighter weight than batteries, that could help improve things like military field operations.
Okay. And the storage of energy is a huge deal.
Yeah.
And a lot of, including with solar and wind, sometimes it's, blasting the sun's really going, but we don't have a high energy demand such as in the nighttime. And so we need more batteries. And if we can store them more efficiently through impurities or through doping of some sort, then it's more energy and less space.
Right. If you've seen the battery arrays for an electronic vehicle, electronic vehicles are great. They're reducing our requirement for fossil fuels, but those are huge battery arrays and they're difficult to manufacture and they're dangerous. So finding new materials for consumer grade batteries or even moving towards fuel cell systems would be preferable.
Yes. And one material that's really prevalent in these batteries is lithium. And so I don't know, do you know if lithium had many use cases before EV, and is lithium the standard for batteries? Do you know?
I think currently lithium, obviously a lot of people are aware of lithium use in batteries because that's what our cell phone laptop batteries are all made out of. And the reason we use lithium is because it's very small and it can move between a cathode and anode really quickly. But there's also work towards like sodium-based batteries, because sodium, I think, is a bit more stable and a bit more abundant. So it'd be cheaper to process and create.
Wow. I've never heard of that.
Yeah.
That sounds that sounds amazing, because sodium is everywhere.
Yeah, you can probably, if you Google sodium ion battery, you'd find some of the research going on.
Okay, might have to do that. Hopefully some of our listeners do that. And you mentioned in 2010 you graduated from undergrad and the job market wasn't so hot. You decided to go into a lab. Was your work before, when you were an undergrad, before you entered a lab, before you went to grad school, did you expect to be working in materials within your undergrad? And you also mentioned in high school you had a particular teacher who really motivated you and gave you inspiration to be a scientist. What did you gain from that course in high school that kind of stands out to you today?
Yeah, so I went to high school in a really small Appalachian town. My high school had about 600 students. It's actually the same hometown as John F. Nash. but we don't need to brag. But a small Appalachian town.
Who's John F. Nash?
He was a Nobel Prize winning mathematician.
Oh, wow. What did he win the prize for?
I don't remember.
Okay.
But, yeah, I think he passed away a couple of years ago, so he was quite old. But yeah, so I went to small town high school, and out of the small pool of students from that high school, just in the year I was there, there's been a number of us who graduated from my class, or 1 or 2 years around me, who all pursued PhDs in chemistry. And that just speaks to how influential this one teacher was. And it was just a class where we learned the textbook stuff, but also a lot of fun benchtop chemistry, basic stuff for high school students. But she was really great at just feeding our curiosity, I think, is what it comes down to. That's keeping us curious and keeping us interested.
That is really, I can't think of a better word than privilege to have at high school.
Yeah, absolutely. I would definitely say we were privileged by her teaching abilities. So yeah, after high school, I decided to study chemistry. And when I started in college, I thought I wanted to go into pharmaceutical sales. And that's only because I knew, like, one of my friend's aunts was a pharmaceutical sales rep, and she made pretty good money. So I thought, that seems fun. But then I had a couple of high school professors who were really good at giving us interesting lab work in the classroom. So we did experiments like one of our professors bought tents from Walmart, and we scraped the paint off the tent poles and tested for lead.
Wow.
Yeah, we went on a trip to a nearby town and took water samples to test for salinity. It was just really interesting stuff like that. Real world application worked in. So I really enjoyed it. I really enjoyed having a problem and then trying to figure out how to solve that problem, then coming to a conclusion.
I can imagine. And then working with your hands and then applying your hands and this manual labor to science. It seems rewarding.
Absolutely. Yeah, but I never imagined myself being like a laboratory scientist.
Working at the scale you're currently working at.
Right.
And so when you entered grad school, did that become when your path towards materials and your path towards electron microscopy start? Is that when it became paved?
Yes, that's when it really started to solidify a bit more. So when I started grad school, I didn't really know what I wanted to do. And part of our first semester process in grad school is interviewing different professors and finding someone who we wanted to work with. And so I basically interviewed, I think we had to talk to 3 different professors, and I talked to 6 or 9 because I just didn't know what I wanted to do. And one of the professors who I talked to, she was a brand new hire. She didn't have any grad students yet. And she had a joint professorship with Oak Ridge National Lab. And if you're not familiar, Oak Ridge National Lab is a facility in Tennessee that was part of the Manhattan Project. They purified the uranium to make plutonium. So it was just kind of a really cool, oh man, having an opportunity to be at a lab facility like that would be great. So I liked the work she was doing, and the potential to, do some work at a facility like Oak Ridge. So I decided to join her lab, and she focused on nanomaterials and electron microscopy. So when I started, I was doing a little bit of material synthesis, so actually being in the lab, grinding things together, and then taking them to the TEM for imaging. But I really enjoyed the imaging part much more. So I kind of just took up residence at the electron microscope and made that my sort of full-time job. And after, I think, about 3 years, we had a staff scientist at the university who maintained the microscope and kept it running while the grad students, destroyed it. And he decided to leave. He got a better position, so he left. And they weren't sure when he'd be back or when they'd hire someone new or what state the microscope would be in. So my advisor said, "Do you want to move to Oak Ridge and work at this facility?" And Oak Ridge National Lab has one of the best microscopy facilities in America, if not the world. So I kind of took a risk and I jumped at the opportunity. And so I lived down there full time for about 3 years, finishing up my grad school work and being able to use world-class facilities to do my graduate studies and finish up my degree there, and met a lot of scientists there who have helped kickstart my career. And so where I am now, it was a very lucky turn of events. So when I was ready to find a permanent position somewhere, it just so happened that at the lab I'm currently working, there was a position available using and maintaining the microscope that I had built a specialty for while at Oak Ridge, which it's kind of a specialized, unique instrument, so not many people know how to use it, how to maintain it. So it was just a really nice turn of events that position became available right when I became available. So it was very lucky that I got where I got.
What an awesome difference compared to graduating for undergraduate for you. And also for me, when I was an undergrad, it took me over 7 months to find a job.
Yeah.
And what about your first experiences versus, grinding materials, preparing the materials? What drew you more to imaging at the initial stages?
I think part of it was just, this is going to sound dumb. Part of it was using really big, expensive equipment. Like, I had never been exposed to that. I went to a really small high school where we didn't have any of that equipment. We didn't, have neat toys. I went to an undergrad where, we had a gas spectrometer that didn't ever work. And being able to use this big fancy tool, just thought it was really fun and exciting. And also just being able to see things at such a small level was fascinating to me. And then we started moving into performing experiments in the microscope. So we bought a platform where you can, heat your sample while it's in the microscope, so you can actually see, how something like heat affects your material. And so not just imaging, but now we're running experiments in the microscope, which was just amazing.
Wow. And most people have never seen an electron microscope before. How large are they? And how do you prepare an image or an experiment with a electron microscope?
So the microscope I use, it's probably about 8 feet tall, maybe
Wow.
2 feet tall. So it's a huge instrument. And we have the microscope sitting in its own room, completely isolated from people, foot traffic, wind, and it sits in a big insulated box. So when you're looking at things as small as atoms, if someone walks by, just the vibrations can obscure your images. If someone's talking in the room, those vibrations can obscure your images. If the temperature changes by a degree, that can obscure your images. So we keep everything very still, very isolated. And we have a bunch of cables that run to the other room where we do all of our imaging and data collection on a couple of computers. So we sit at a computer and the microscope sits over in the other room, and we can there interface with the microscope, acquire images. If we want to apply heat, we can apply heat. If we want to apply an electrical bias across the sample, we can do that all from our little control room that sits isolated from the actual microscope.
And so when you apply heat, would it be to the entire box that's the microscope is encapsulated in?
No, so we have little sample grids. So our sample sits on like a 3 millimeter sized sample grid. And when we heat, we have a special heater that will heat just that little area.
Okay.
So it actually works through resistive heating. You apply a resistance across a membrane, and that creates heat. So it's very controlled. Instead of having to heat up, a whole microscope, we're just doing the sample.
Okay. That is a intricate process.
It's tricky, and those experiments take a lot of time and a lot of forethought, because one heating sample grid costs about $100. So if you want to run an experiment, you better know what you're doing, because you don't want to just waste $100 by not being prepared, by not having thought through what you're doing.
No. But it doesn't function on the first try, I'm guessing. I'm guessing you do multiple iterations of a image or experiment.
Yeah. Well, so when we acquire data, it usually takes about an entire day to get everything we need. So, an 8-hour session on the microscope to gather data, get everything aligned, get the optics working properly, and then collecting data and just basically acquiring as much as we can get throughout the day. Just so, I don't know, if you don't, sometimes if you think, oh, okay, I've got enough, I'm going to leave. Then you get home and you start analyzing, and you're like, oh crap, I wish I would have gotten this, or I wish I would have, I needed this piece of information. So yeah, we're pretty thorough in acquiring our data, and how much, we sit there for a couple hours and get different sizes and scales and different spectroscopy, so we can see just a thorough analysis of what we're looking at.
And for in that case, in that context, it's better to have too much data than to have not enough, because then you'd have to go back and do another sample, another $100, another, possibly an entire day of imaging, correct?
Oh yeah, it's always better to have more data than you think you'll need. I mean, I say the grid costs $100, but the cost of our labor is way more than that. So if we have to go back and do it again, that's a big waste of money.
Yes, being quickly with, I mean, science is slow and messy, but making it slower is not, is, we want to avoid that.
Yeah, the management frowns upon that.
Yes, yes. As as I've heard, the bean counters frown upon that.
Yes.
And so were you in charge of maintaining this system, this electron microscopy system for 3 years, or maintaining it? Is that the position you moved into at the last 3 years of your graduate studies?
No, when I was in graduate school, I was just a user on the microscope. So there was a staff scientist who would maintain the microscope. So I was at Oak Ridge for 3 years for my graduate studies, but then I stayed there for 3 additional years as a postdoctoral researcher. And so the microscope I use, the name brand is Neon, Nion, and it was developed by 2 gentlemen. And my postdoc advisor was basically kind of unofficially their grad student. So he really knows these instruments. And so I worked with him for 3 years doing our own research project, but also I got to see a lot of the behind the scenes, digging into the hardware and the software, replacing boards, replacing, whatever fails on the microscope. So the position I'm in now is similar to that. So we have this Neon microscope, and I'm the primary caretaker of the microscope at the lab. So if anything goes wrong, either I have to fix it or I have to diagnose it and then call the company and say, hey, this is busted. And the company is based outside of Seattle, Washington, and we're on the East Coast. So they don't like to just fly out here too often. So frequently, if something's broken or busted, they'll send me parts. Then I'm in charge of swapping out parts or putting in a new electrical board or switching cables. So it's a really fun aspect of my job where I get to be a bit more hands-on with the microscope instead of just a user of the microscope. But it's also intimidating because if something goes wrong, people are calling me saying, hey, what happened?
Maintaining systems is very intimidating.
Yeah.
Operating them is, it can be difficult. Installing them usually isn't too difficult because everything's either it does work or it doesn't work. And usually it's not the installer's fault if it doesn't work. It can be, faulty something. But maintaining it, that is, anything can happen.
Oh, yeah.
And if you're working on a part that maybe, I don't know, if luckily you had that experience with your previous postdoc,
Mm-hmm.
and that gives you, you could see him, and he was a graduate student of the creators, so he had a lot of experience. So it's understandable why you got your position you got now, because it is not simple or really, I would say, difficult.
Well, I think a lot of it's intimidating. It's
Yes,
a
it is.
very expensive piece of equipment, and people are afraid of breaking it. And I sort of know how far I can go without doing incredible damage to it. So, I'm not afraid of pushing buttons and pulling cables, whereas other people might say, I'll call somebody else to do it.
And that's, you have the experience and the experience that allows you to have the confidence to do that.
Yeah, I don't know if I'm confident or naive.
Oh, at some degree, it's a little bit of the same.
Yeah.
So, Bethany, are there any parting words or any last thoughts you'd like to leave our audience regarding science, regarding chemistry, regarding materials, regarding going into, the pursuit of what people want to do?
So the one thing that comes to mind is I was listening to a different podcast earlier today, and there was a woman who was complaining about NASA funding. And she was saying she doesn't understand why a facility like NASA would receive $57 million a year when people are starving in our country, schools don't have proper food for all their students, everyone's reading on a sixth grade. The average reading level of Americans is a sixth grade reading level. We obviously should be investing in ourselves. And she didn't understand why we're investing in space exploration. And that sentiment really hit me hard because a lot of the work I do, someone might look at it and say, why are we investing, millions of dollars in moving atoms around? This is very silly. We should be feeding people. And to an extent, I agree. We should be investing resources in taking care of our people, but also basic science research is going to benefit us as a society in the future. And we have to look towards our future. We can't just focus on the now. We have to think about the increasing demands in our electrical grid, how we can reduce that, and not just be so nearsighted to say we shouldn't be pouring millions of dollars into these programs. There's better uses of our money.
My guest today has been Dr. Bethany Hudak. Thanks for coming on the podcast, Dr. Bethany.
Thank you.